All right. Welcome, everyone. Thanks for coming along to the webinar today. Um, so I'll just go ahead and get started since it's a pretty quick one we have for you. My name's Megan, and I am the training coordinator here at NeSI. Today we're discussing job scaling and running tests. And Anthony from our app support team will show you how running and reviewing scaled down jobs can help you determine what resources you should request for your full-size NeSI jobs. So I will just go through a bit of housekeeping and then pass you guys on to Anthony. So Anthony will be presenting for about 30 minutes, followed by 10 minutes of questions. And we just ask that you keep your audio on mute if you're not speaking or asking a question. If you have a quick question, you can type it into the shared Google Doc, which you see the tiny URL there, and I'll post the link in the chat now. Just 1 second. There you go. So if you go to that link, you'll see the shared Google Doc. Ask any questions in there during the webinar, and we'll try our best to answer those. Otherwise, you're welcome to ask a question verbally at the end during our Q&A. Lastly, the webinar video, slides, and the Q&A document will be available on the NeSI website. And so if you don't want to appear in the video, just make sure that you don't have your video turned on. And that's all the housekeeping. I'll just go ahead and pass you along to Anthony now so that we can get through the good stuff. There you go, Anthony. Yeah.
Hi, so as Megan said, I'm Anthony. I'm application support for NeSI, and I'll present this webinar. So, as she said, it's just a quick little webinar on scaling and running test jobs and how to estimate resource requirements for your jobs. So, in this webinar, we're trying to cover 3 main areas. The first of it is to investigate benchmarking or scaling down your jobs and how to scale up your jobs. The second part is looking at using the sacct command to analyze your job results. And the third thing we're trying to look into is using the results from that sacct command for predicting or scale up your job's resource requirements. So why exactly is it important for you to understand scaling or benchmarking? Well, one of the big reasons why it's important to understand this is because on our HPC platforms, you'll be doing your work differently to how you're probably used to doing your work on your local machines. So if you were on your local laptop or desktop or maybe a local server, you're probably used to an environment where you open up a piece of software, you can interactively write commands, or maybe you just tell it to run a whole script through, and it will requisition the resources it needs from the system, or maybe if you're submitting to a server, maybe you do need to specify the number of CPUs, but it will run for as long as it needs to run for, use as much memory as it needs, so long as it's available in the system, and finish when it finishes. With the NeSI HPCs, there is essentially a prerequisite that you at least have some general understanding of the basic dimensions of your jobs. So you should have a knowledge of how long your job's going to run for, how much memory it will need, and how many CPUs it will need. And this is because when you submit jobs on the NeSI HPC systems, you have to specify those requirements at submission. And if your job needs more than what you've specified, then it's likely to fail. And so what this means, if you just try to submit your full-size scaled-up jobs straight from the get-go on the NeSI HPC systems, is that there's a fairly good chance that your job's just going to fail, and it's probably going to fail after maybe queuing for days or weeks, depending on how big your job is and what partitions you're trying to use, what resources you're trying to use. And it might run for a few days or weeks, depending on how long it is, and then fail. And so unless you're doing some kind of checkpointing or something, all that information will be lost and you won't be able to use it, and you'll have to rerun other jobs, and it'll just be trial and error for these really long jobs, and you're going to waste a lot of time and resources just to be able to get your full-size jobs up and running. And so that's where scaling comes in and why it's important, because if you can scale down your jobs, you can do benchmarking of your jobs, you can potentially save a lot of time. So what exactly do I mean by benchmarking? And how would you do benchmarking? So benchmarking is essentially a small reproducible test case of your job, with the idea of it being essentially as much alike as your full-size, full-scale job or scaled-up job as possible, so that you can run a small-scale job to try and estimate how many resources it will need. Ideally, these jobs will be just a subset of the data you have. A lot of scientific software, a lot of scientific programs that you'll be running, your scripts you'll be running, you'll probably have a large data set. Hopefully, you'll be able to subset this data set to a much smaller size, a size that can be run in a much more reasonable amount of time. In which case that would be the ideal benchmark, or the ideal scaled down version of your job. But that's not necessarily going to be possible in all circumstances. You do have another option for scaling down your work, though it's not near as good as being able to just scale down your data, because when you scale down your data, you can be relatively confident that it will either proportionally decrease the runtime of your job because you're decreasing the data, or decrease it in a manner that's easily predictable by some simple calculation. So maybe, halving your data will quadruple the speed at which it runs, or something along those lines. And it's something that you can easily, quite easily plot. Whereas the other option is to scale down the code itself. And so you could potentially go into your script and comment out a few of the lines of your code to try and make it so that it can run in reasonable time. This has the major downside of you don't really know what lines in your script are causing the major computational consumption. And so if you comment out some of these lines, you can make it run, but you don't really know how much of a proportion you're getting rid of. You can overcome this a little bit if you use some profiling tools, and we do have some documentation on profiling, and there was a webinar on specifically Python profiling that was done. I won't go into too much detail. I won't go into any detail on that because we do have other stuff for that and really deserve its own webinar, which is why it has it. But as I said, if you look up profiling either on our documentation pages, or if you just Google profiling with relation to whatever scientific software you're using, you'll be able to find something, usually. The downside is that you do have to run through your script to be able to see what parts of your script are using what computational resources. And so if you can't actually run through the whole script, even when you scale it down as much as possible in a reasonable time, you're still going to end up with you not really being able to do the profiling. The other thing is, ideally when you do profiling, so ideally you've got your subset of your data, which is able to run in a more reasonable time. And ideally it's small enough now that it can actually run on your local machine or your server or whatever you have available to you. The reason why you want it to be that small, if possible, is because then you can actually submit it to your local machine where you don't have the restrictions of needing to know in advance how long it's going to take and how much memory it's going to use. And it will just requisition from the system, and you can use the results of it running on your local machine, so how long it ran on your machine and how many CPUs it used and how much memory it used. And you can use those results to actually use it as your starting point for when you run the jobs on our platforms. So if you know it runs for 10 minutes on your personal laptop, you can use 10 minutes as a starting point there with X amount of memory for having so many CPUs. If that's not possible, and that won't always be possible, that's okay. So this is why we're scaling down. So if you were doing your full-size jobs and you were in this situation, you just have to do trial and error. And you still have to do trial and error, but doing trial and error on large-scale jobs can take days or weeks, depending on how big they are. But by making them as small as possible, you should theoretically have been able to make the data, you should theoretically be able to run enough tests in a short enough amount of time that it's not unreasonable for you to do it. So the main thing about this is that you're wasting a bit of time and a bit of resources now in order to try and save some time and resources later. That's the biggest thing we wanted to probably take away doing this benchmarking with the scaling. So how large should your benchmarking job be? An ideal rule of thumb, I guess, is around 10 minutes. This isn't a very hard and set rule. 10 minutes is a good idea because if you do it shorter than that by a significant amount, depending on what you're doing, you could have job overheads that take up a decent proportion of the computational time. So job overheads like reading in the data set or reading in some packages. If your job's too short, and they take up a lot, and those overheads take up a large amount of time, they can kind of skew your results a little bit. That's not usually a problem, so it's okay even if it's only a few minutes long as well. It's okay if it's a bit longer than that as well. It doesn't need to be. It's not a hard and fast rule. It's also good to make it short because it means you queue faster and your job starts and runs faster, and so that's always a benefit. Another tip for when you're doing these benchmarking things is if you are able to put some kind of line in your script. That means it will let you know how far through it is every point. So maybe it prints after every iteration or something like that. Because that way, when you look at the logs after your script's done, even if it fails, you can see how far through it was, and you can use that information to help you determine how much you need to increase your first benchmarking job. So now let's take a look at an example. So in this, or a few parts of an example, in this we're going to use a multi-thread job initially. And so I won't go into too much details about what the job is doing, but it's essentially creating some data, and it's sending that data off to, splitting that between the threads, between the CPUs, to run through some processes and gathering it back up and doing some more calculations. The full size data is going to be 60,000 iterations, 60,000 normal distributions. But say we're in a situation where that 60,000 is just too big. It's too big for us to run on our local machine, and we don't really want to be testing something that size because it might take us a long time, given how large it is. And so we've scaled down our data, and we've decided we're going to try scaling down 5,000 iterations rather than 60,000. This is only about half of that. So, but when you're doing it yourself, it could be orders of magnitude. It could be, 100 versus 1 million or something along those lines. And so for this one, what we'll do is hopefully it would have been able to run on our local machine, ideally, with 5,000 iterations. And we would have some results from our local machine of how long it took to run and on however many CPUs we used and how much memory it used. But if that's not the case, we will just run this a few times with guesses, our best estimates that we can come up with. And if they fail, we'll keep doing it until we get it right. This is a small scale job, so it's okay to have them fail because failing here doesn't matter. These are only a small amount of resources and a small amount of time you're wasting. And we're okay with wasting a bit of resources, a bit of time now, so that you can save it later. And so once we have a job that's up and running, and so let's say that we decided we get it finally running in 10 minutes with 1,000 megabytes of memory, for a 4 CPU job is what we decided to start with. That's what we do. So let's take a look at the results of a job. So we'll be looking at the results. So we've managed to get it to run. And now what we do is we look at the results with the command sacct. So sacct is a command which will by default give you the outputs, the results of all the jobs that you have submitted, are running or ran since midnight tonight, I believe. You can make it so that it tells you older jobs if you want to. So you might be looking at some older jobs previously that you were going to analyze now, and you can do that with the flag -S followed by the date in the format year/day month. Sorry, year-month-day. And so when we look at the output of these jobs, this is just a single job, a single 5,000 iteration job. The 3 columns that we're going to be wanting to look at are the elapsed column, the alloc column, and the max RSS column. So the elapsed column tells you how long the job ran for. the alloc column tells you how many CPUs, logical CPUs your job had, and the max RSS tells you the maximum memory that your job used at any one point. So you can see from the output here that there are 4 rows. This is because it prints out all the multiple steps of a job. You're concerned mostly about the highest of any of those columns. So if you just look at, that's the top one for elapsed and alloc, and max RSS will usually be one of the other ones. And so in this case, we can see that our job ran for 3 minutes and 17 seconds with 4 logical CPUs, and it used about 0.4 gigabytes of memory. And so from this, we could potentially just take a guess about how many resources our larger scale job will take and assume that it's going to scale linearly, so that we're going to, as we increase the amount of iterations, the size of our data, it's going to scale linearly, or and maybe that we assume that the memory scales linearly. And maybe we also assume that if we increase the amount of CPUs, the time will decrease linearly, so it will half if you double the CPUs. This isn't necessarily going to be the case. So it can be all right, but it's not always going to be right. And so what we really want to do is have multiple of these tests at different data points. We want multiple different data points so that we can plot together so that we can extrapolate out an estimate. So first things first, we're going to look at iterations. So we're going to increase the number of iterations and do a few jobs with different iterations. And we'll do 10,000, 15,000, 20,000. I won't show the S account output again. I'll just show you what it looks like when we plot those results. So for each of those jobs, we'll assume that we managed to get them run. What we would usually do is we would assume linearly scaling for each of these jobs because they're all still small, so it's okay to waste a bit of resources. And if they fail, we will just increase the resources a bit until they succeed. They're all hopefully going to run relatively quickly, so it doesn't particularly matter if they fail. But a starting point for these small scale jobs is just to assume everything scales linearly, that as you increase the amount of data or whatever, that it's going to increase the amount of time linearly and the memory linearly. So this is the plot of the outputs of the DS account outputs for these 4 iterations. So 5,000, 10,000, 15,000, and 20,000 iterations. So the first plot, well, actually, let's look at the plot on the right first. We have plot of iterations versus the memory, and so it's for 4 CPUs. And if we look at that, we can see that it looks like regardless of the amount of iterations we use, the memory seems to stay relatively stable at about 400 megabytes of memory. This means that theoretically, if we increase the iterations up to 60,000, we shouldn't have to increase the memory. It should still be stable at around 400 megabytes. But as a rule of thumb, for both memory and wall time requests, you'll want to ask for a bit more memory and a bit more time than you actually expect to need. This is just to avoid the fact that sometimes some nodes will run slower. And also S account doesn't measure memory continuously, but measures it in 3-second intervals. So what this means with S account is that you could potentially miss out on some of the higher memory spikes, and so you're not going to usually detect exactly the highest memory. It's usually pretty close, but it's usually not exactly the highest. And so a good rule of thumb is 20% more memory and time than you actually expect to need, and that should be fine enough that you won't have to worry about it failing on a random node that just happens to not be as good, or because it didn't detect the spike in memory. Won't work 100% of the time, because some people's work will have very, very spiky memory that's not easily detectable. In that case, you'll just have to do a bit more testing to see, but most people's it will work. And so now, looking at our other plot, we've got a plot of the iterations versus time. So that's the size of our data, the iterations. And now we can see here that as we increase the iterations, it seems to relatively linearly be increasing the amount of time it takes for your job to run. And so that was, as we, we're just using as a rule of thumb to start with, and it looks like it turned out to be right in this case. Given how close it is to just being every 5,000 iterations increased by 200 seconds, you could just use that and say that if we increased it up to 60,000, it would be okay to just say it's going to take about 12 times longer. However, perfect, and want it to be nice. Take the mean of the times, so the various times for each of these points. We have a point here at 200 seconds, another point near 400, and so on and so forth. And you divide that by whatever the iterations is for each of those points. So 200 over 5,000, 400 over 10,000, so on and so forth. You take the mean of that number, and then you would multiply that by however many iterations, or however, the size of your data that you're looking to do. In this case, it would be 60,000. And so the mean of that number is actually 0.039. And if you multiply that by 60,000, you can then estimate that if you were trying to do the full 60,000 iterations with 4 CPUs, it would take about 40 minutes. And so from this, we can assume that a 4 CPU job would take about 400, well, you'd probably ask for about 500 megabytes of memory, and it would take about 40 minutes to run. However, maybe that's too slow, or maybe 4 CPUs isn't necessarily going to be the optimal amount of CPUs that you want to use. We started with 4 CPUs, but that's not going to necessarily be the optimal amount of CPUs. And so we want to know where the ideal number of CPUs is for us to run our job. And so to do that, we're going to have to do some more scaling tests. We're going to have to do some more benchmarks. So we're going to make some more small-scale jobs at varying numbers of CPUs, just doing the same thing as that we've done previously. Hopefully, we will just assume that it scales linearly here again. So if we double the CPUs, we will double the time, asking for about 20% more. And then again, if they fail, as I said, you just run them asking for more until they succeed. These are really small jobs. They only take a few minutes, so it's okay if they fail. You can always run them again, and it's not much resources, time wasted. And so for us, we're going to look at CPUs 2, 4, 6, 8, 10, 12, 14, and 16 CPUs, and we're going to plot the results the same way that we've done here. But before I get on to the results, plotting the results, I'm just going to have a quick talk about nonlinear speedup. So our other examples have been relatively linear in their speedup, but CPUs, you will never see a linear speedup as you increase the number of CPUs. There are other contributing factors to why this won't happen, but the major contributing factor of why you won't see a linear speedup with increasing the number of CPUs is something called Amdahl's law. So Amdahl's law describes the fact that there's a split in your work when any work you run on HPC, which is part of it is parallelizable, part of it's parallel, and part of it is serial. And so you can imagine a situation where the parallel part of your work, usually, if you tried running it on a CPU, it takes up the majority of, on a single CPU, it takes up the majority of your time. However, as you add more CPUs to your work, that parallel part of your code goes faster and faster and faster. And it could theoretically be increasing perfectly. So doubling the CPUs doubles how fast it runs. And so the more CPUs you run, the faster and faster it runs. Assuming that there's no other nonlinear thing causing it, effect causing it not to speed up linearly. That's a big if, but just for the hypothetical. But that serial part of your code, that's only benefits from one CPU or having that CPU be better, right? And so when you speed up the parallel part of code, it's getting faster and faster and faster and taking up a smaller and smaller percentage of the compute time. The serial part of your code is staying the same. It takes just as long with 100 CPUs as it takes with a single CPU. And so because of that, as you increase the number of CPUs, the proportion of time taken just on the serial code goes up and up and up, and it leads to this asymptotic curve you see here of speed up, where increasing the processes will have a lower and lower return on investment the more you add, because that serial part of your code, there's a minimum amount that you can get the speed down to, because it's once you've gotten the parallel part down to essentially 0, the serial part still is the same.
Can you move that? Yes. Away.
Was that visible?
Yeah.
Oh, great. Sorry, I didn't know this was visible. Let's get this out of the way. So I won't show you sacct again, because it's just a lot of the same and it fills up our page. But here are plots of our outputs from sacct. So we've done the same thing for all of those jobs, all of the different CPUs. We've assumed it scales linearly, and if they fail, we ran them again until they succeeded. And now we've plotted them all, the results, the max RSS, and all the other things on these plots that we're going to show you. So the first, these two plots here are actually the same data in this case. The first plot is just the time versus the logical CPUs, and the second plot is the time versus the log2 of the logical CPUs. I've decided to put the log2 of the logical CPUs in here because it just makes it a little bit clearer for you to see that scaling behavior of the asymptotic reduction. So as you increase the number of CPUs, you theoretically, if you were having a perfect scale up, perfect speed up, doubling the CPUs would double the speed. And so with the log2 of the logical CPUs, that would be just a straight line because you double the CPUs and then double the speed. And so because log2 would just be a nice straight line. But you can see on the log2 graph that it's curving and it's leveling off at the end. And so there's a point where as you add more and more CPUs, that the return on investment, so to speak, of adding those CPUs no longer becomes worth it from ours or your perspective for you to keep adding those CPUs. And so your job will maybe run faster, but the cost of that extra speed is much higher than the cost of previous speed up. So looking at this, if we were going to choose a CPUs for us to decide that's ideal, here we can see based on that curve, I mean, 8 might be a good number of when the curve starts going on. But you could theoretically, if you wanted to, go all the way up to like 12. It's really 14 and 16 that you can see have very bad speed ups. If you look at them here, 14, 16, 12 is still not unreasonable. And so we'll choose, in our example, we'll decide to go with 8, but as I said, there's not really a hard and set rule about how much speed up you should be having for the amount of CPUs you add. If you're still getting, so the 8 I think has like 90% speed up still, but if you're still getting 70% speed up, that still seems relatively reasonable for adding the CPUs, and so you're still probably getting that around the 12 CPU mark. But as I said, we'll go with 8 for ours as the, yes, we'll go with 8 for ours here as the amount that we want. And now taking a look at the plot of the memory versus the logical CPUs. Here we can see that unlike the memory versus the iterations, it does seem to scale linearly against the number of CPUs. So as we increase the CPUs, it seems to almost proportionally increase the amount of memory. There is one point that's a bit of an outlier, which you can see with point 10, just here. That's probably not anything to worry about. That probably just goes down to the nature of sacct not measuring memory continuously, taking up 30 seconds intervals, and probably just unluckily detected low memory there. So here, because we know that 8 CPUs is the amount of memory that we are looking to use, the amount of CPUs we're looking to use, we can just look at what memory usage was being used at 8 CPUs. And so we can see that it's about 750-ish megabytes or 0.75 gigabytes of memory. However, in the event that the amount of CPUs you decide you want to use isn't being recorded here because you extrapolated it out, you can just either extrapolate it out with some kind of plotting command in whatever software you're using. I won't tell you what software to use for these plots because you can use either R or Python or anything you want. You can even do these by hand, or you can just, if you're doing it by hand, you can actually just do it out by hand. These don't need to be completely exact. They're just good. All these basic scaling things are mostly to get you into nice ballpark ranges of what you actually need. Otherwise, you can do similar to, or if you want it to be completely accurate, you can do similar to what I said before, where you take the mean of the memory over the mean of the logical CPUs, and you multiply that by how many CPUs you think you're going to need, and that will give you a good estimate of how much memory you need for that many CPUs. So from all of this, we think that our job is ideal at 8 CPUs, and at 8 CPUs, we think that it's going to need 0.75 gigabytes. The reason we think it's going to need 0.75 gigabytes for a full-size 60-other iteration job is because the 8 CPU job used about 0.75 gigabytes, and it didn't scale, memory didn't appear to scale with iterations with the size of the data. And so with this being about 12 times longer, we could just multiply by that, or we could have done the math. Either way, it works out to be close enough to 21 minutes long is how long we think the job's going to take. Because this, again, with these numbers, we're not going to put exactly 21 minutes in. We're not going to put exactly 0.75 gigabytes in, because that's not really a good idea. If you want to have your job succeed, you want to ask for a little bit more time and a little bit more memory. So in our full-size job, we're going to ask for about 20% more, just round it over to 30 minutes and 1,000 megabytes of memory for our 8 CPU jobs. And we will submit that, and hopefully it will succeed. So let's take a look at the results. So when we ran this job, we can see that it actually did run for almost 21 minutes exactly, 20 minutes and 34 seconds, and it used almost 0.75 gigabytes of memory. But this is a really good reason why you would want to ask for more time and memory, because we got our estimates here were very accurate, but that variation in the CPUs means that it could have been on a slower CPU, and so it might have run for 21 minutes and 30 seconds instead of 20 minutes and 30 seconds, which would have killed our job. Or it could have asked for more memory than it has available, which would have also killed our job. And so just as a rule, you will want to ask for a bit more memory and time than you expect. One more example that we'll just try and go through is MPI, an example. Very similar to what we were doing in our OpenMP one, except this one will be splitting these tasks between, it creates a list of 60,000 numbers, splits them between our tasks. Some calculations done there, gathers them back together, and then sums them. Again, we make our initial estimate the same way we did previously, where we run the job on our local machine if possible, and if not, we get it as small as possible, hopefully by subsetting the data and running it a few times until we get one that succeeds, and then once we have one succeeds, we'll use that. So this job would use, and that's the bash script that we'll use for it. One thing that we'll do a bit differently than what we did with the OpenMP example is that in the OpenMP example, we used iterations first. We'll do CPUs first this time. The reason you might want to do CPUs first, it's not a big deal, it doesn't matter majorly. But if you do CPUs first and find the optimal numbers of CPUs, then you're using the optimal numbers of CPUs to do your iterations or your data scaling tests, which means those data scaling tests can potentially run a bit faster, whereas the CPU scaling tests, you'll always be using the smallest amount of data if you can. And so those won't run any faster. The iteration ones will hopefully run a bit faster because of that. So this is the first plot. Here, it's the CPUs versus the memory per task. We can see that the memory per task seems to be remaining the same. Remember, this is an NPI job, and so because it's an NPI job, it needs to use mem per CPU when requesting your memory. And what that means, and that's because each task requires its own separate memory because they're distributed. And so as you increase the number of CPUs, you will inevitably linearly increase the number of memory at least. But this plot shows that other than that normal linear increase in memory based on the fact that it's NPI, you don't need to worry about some kind of non-linear increase because of extra CPUs. And so looking at this, you will use about 200, well, you'll need about 175-ish megabytes of memory, which is about, we'll round up to 200 for our tests. And then when we ran plots of the plot of the time versus CPUs and time of the log CPUs, looking at the log one again, you can see that it's probably at the 5 CPU when it starts curving away and leveling off. And so that's where we will assume our best CPU usages. And so we'll go with 5 physical CPUs. So this is physical CPUs. The previous example using logical CPUs because MPI tasks do not share logical CPUs. So you're always dealing with physical CPUs, which there are 1 physical CPU for 2 logical CPUs. Another thing to be aware of, just because it's MPI, is Amdahl's law is the main contributing factor for most scaling behavior. MPI also has an additional factor that causes more nonlinear scaling behavior that's not present in OpenMP, and that's the fact that the communication across MPI is not free. It's not computationally free, and so the more tasks that you have in your job, the more communication overheads you have, and it means that you level off. You reach that leveling off of speed up faster for the same work if you're doing it MPI versus OpenMP shared memory situation. And finally, now that we've decided what the optimal number of CPUs are, and we've decided and we've seen how the memory scales, that it doesn't seem to scale with a number of CPUs other than the MPI sense doesn't seem to scale without memory per CPU. We can look at how it scales with iterations. And now when we run these jobs, again, you run them at their small jobs. It's okay if they fail. You assume linear scaling to start with, and then you adjust based on the results you get. With the plot, we can see that the time does seem to scale linearly with the number of CPU, with the size of the data, and the memory seems to be stable with the size of the data. So we don't have to worry about any scaling issues with the memory there. This means, so again, you could just do the one-to-one situation where you go, oh yeah, double the amount of data, double the time. But if you want to be, again, more accurate, you just do the calculation that I mentioned where you take the time, the means of the times over the seeds. So in this case, 500 seconds over 5,000, and then just 900-ish over 10,000, and take all those, take the mean of that, and then multiply it by the full size job that you want to run. In this case, 60,000 is the size of the data. And we can see from that, because the number is 0.091 is what we get, that if we do it for a 60,000 iteration seed data job, it would take about 1.5 hours with 8 CPUs. And so this is our last job. We're going to assume it's going to take 1.5 hours because of how we did the scaling. We're going to assume it's going to take 0.7 gigabytes of memory per physical. Actually, got to fix that one. I just made a mistake. I just realized 0.7 gigabytes of memory per task, not per physical CPU. And that will be, and so we'll run this job. We'll increase it by a bit, saying memory per CPU. That should be 105 megabytes of memory per CPU, not 210. And we'll ask for 2 hours rather than 1.5, just as a rule of thumb. It doesn't have to be exactly 20%. There's no expectation of that. And this is for a 5-task job to run our full 60,000 sized iteration data. So when we look at the results, we can see that our estimates seem to be relatively correct. This one took 1 hour and 28 minutes on the 10 CPUs and used about 0.17 gigabytes of memory at the maximum. And that's the webinar done. First, I guess, are there any questions?
Well, I was interested whenever I first listened to this presentation about how this affects fair share, or knowing this sort of information, what resources to ask for, how it affects your fair share score?
Yes, so it can be useful in knowing that as well. The reason is because if you ask for too long of a job, it won't matter about your fair share score. When your job finishes, even if your job doesn't use all the time you asked for, those resources are all freed up again. So you're not charged for time you didn't use. However, if you ask for more memory or more CPUs than you need, your job will be charged for those resources. And when we go for renewals on our team, we will generally look at what you actually needed when we're deciding how large of an allocation to give you, not what you ended up using. So if you have jobs that are requesting 10 gigabytes of memory per CPU, but you only appear to be using 1 gigabyte of memory per CPU, we're going to give you an allocation with the expectation that you're going to need only 1 gigabyte of memory per CPU. And so that will mean that when you get an allocation, you'll run through it faster. And even if you have an allocation, you'll always run through it faster if you're asking for incorrect resources. But if you make your resources more correct, you can burn through your allocation more slowly, and means you'll get through it faster. It also means you'll queue in all areas faster, not just because of the fair share score, but because any job that's smaller will, on average, fit in more places. And so it will run faster.
Awesome. Any other questions from the group? We'll just go ahead and...
Hello?
Yes, question?
Oh, sorry. Yeah, I do. I have one. Thanks, Anthony. That was great. Really enjoyed it. I was wondering, could you explain the difference between a physical and a logical core?
Sure thing. So for those of you who aren't aware, on our systems, we have something called hyperthreading enabled. And so what hyperthreading means is that we have something called 2 logical cores for each physical core. And the way you can think about a logical core versus a physical core is if you imagine a standard computer with a standard physical CPU core, when you're running jobs on those standard physical CPU cores, you usually have only 1 thread per physical CPU core. Mm-hmm. But what can happen when you're running jobs on those physical CPU cores is that sometimes those threads will stall for whatever reason. And so maybe they're waiting on data to be written, or maybe they're waiting on one of the other threads to finish a calculation so it can use that number, or anything. It's waiting on something and it's stalled. And so that's wasted CPU time when you have that thread just sitting there, not doing anything. One way around this is that you can put multiple threads on a single physical CPU. And so what this means now is that when one of those threads stalls, that stalled thread can be kicked off, and an idle thread can now jump on and start running through its work. The thing is that switching of threads from a stalled thread to an idle thread is not computationally free. There is computational cost between threads, and so you might not necessarily actually get a performance increase from having multiple threads on CPUs, but a performance decrease, because the savings from being able to switch to idle threads is less than the cost of having to switch between threads. What we have is this hyperthreading system, which means it's a hardware and a software thing, and it means that we have 2 hardware threads per physical CPU core. And so these 2 hardware threads, they can each store a thread. Only 1 thread can run on the CPU at a time, but you have 2 threads stored on the CPU, essentially. And so now, theoretically, when one of these threads gets to a point where it's stalled because it's waiting on something, it can then switch, theoretically, computationally for free to the other thread, though it doesn't always seem to be the case. It's supposed to be, but it doesn't seem to be the case. Switch to the other thread and start running, and you don't have that cost associated, or as much of a cost associated with the switching of the threads. But what this also means is that Slurm doesn't understand our understanding of the CPU. It doesn't have the same understanding. Its understanding of the CPU is the lowest unit of computation, essentially. And so because we now have these physical threads, these hyperthreads, the logical cores on each physical core, it now considers the lowest unit, the logical core, to be the CPU. And so now when you look at things like mem per CPU or CPUs per task or something like that, it's no longer referring to physical CPUs. It's referring to logical CPUs, because that's the lowest unit of computation. Another way of thinking of it is you can imagine that the physical CPU is a calculator, and the thread being a student in a math class. And usually you might have one student with one calculator in a math class, and then they are stalled when they're reading their math book to go on to the next question. Hyperthreading is essentially sharing a calculator between two students, two threads, and allowing them to switch between who's using the calculator and who's who's reading the textbook. Did that answer your question?
It does, yes. But then one thing is, why do I need to specify in an MPI job the memory per CPU? Why can't I just allocate a general CPU like memory?
Yeah, so with a MPI job, if you're specifying whole nodes and you're specifying tasks onto nodes, you can actually specify just with --mem. But if you're just specifying in tasks equals whatever, and you're not forcing them onto a single node, what will happen is that those tasks can potentially be some of them on the same node, some of them on different nodes. And what will happen is that if they're all on different nodes, it's fine. They'll all get 1 gigabyte of memory if that's how much memory you ask for with --mem. But if they're all on the same node, they'll only get 1 gigabyte of memory together.
Yeah.
And so that means that if they have a shared, you have to ask for pretty much as much memory as you're going to need if they were all on the same node in that situation. And obviously then if they all get split up, then you're getting a whole lot more memory than you actually need. By saying memory per CPU, you're saying wherever the CPUs are, give each of these CPUs this much memory. And so because tasks will be, if the tasks are spread across multiple nodes, then one task on one node and two tasks on another, and each of them say have 2 logical CPUs each. The task that has 4 logical CPUs on it from the 2 tasks will get twice as much memory as the node that has 2 logical CPUs from one task.
Yeah. Cool.
Any further questions?
Not for me.
All right, then. I'll just go ahead and wrap up because we're a little bit over time. So let's see. If you do end up having questions, just know that emailing support@nesi.org.nz at any time is the best way for you to get in contact with our support team. There's also documentation available and a recording of this webinar, and the slides will be available on NeSI's website in the next few days or so. So look out for that. And if you are a fan of webinars, we have 3 more before the end of the year. The content of those webinars are on your screen at the moment. So if any of those look like they'd be of interest to you, mark those dates in your calendar. And once again, information for those are going to be on the NeSI website. But that is it from us for the moment. Thank you all so much for coming, and that's the end of our webinar today. And have a great afternoon, guys.
Thank you.
Thank you.
Thanks for coming.